All right. Today we're going to be looking at trigonometric identities, and we're going to start with a little bit of brief review because some of these you've already seen before. So for example, reciprocal identities. These are just the identities of cosecant and secant identified as what they are really. 1 over sine of theta and 1 over cosine of theta. We've seen these before. A little bit of old hat there, if you will. Tangent identity, cotangent identity. We've also seen this before. Again, basically definitions of what tangent and cotangent are. Tangent of theta is sine of theta over cosine of theta, and cotangent of theta is simply the reciprocal of that. It is cosine of theta divided by sine of theta. I'm moving quickly because we've seen this. Negative angle identities. We've looked at this as well. This is really a question of, are these functions even or are they odd? Look at this guy here. Sine of negative theta equals negative sine of theta. It's really just a question of is this even or is this odd? Remember, if a function is odd, you will see that f of negative x is equal to negative f of x. Notice I've got sine of negative theta, basically f of negative x, is equal to the negative sine of theta, negative f of x. This is true for both sine and tangent, as both of those functions are odd. And basically this identity is just telling us that these functions are odd if I know what the input is for the negative theta. I can figure out what the input and output would be for using negative sine of theta. Similarly, if I have cosine, I know that's an even function, as f of negative x is equal to f of x if it is an even function, and we've seen that before. So again, a little bit of review here. Here's a new one. Pythagorean identities. Basically what we're going to do is we're going to prove that sine squared, let's look at the first one here for starters, sine squared theta plus cosine squared theta equals 1. And if you think about it, it actually really makes sense. If you have a unit circle, there's my unit circle, I know it's fantastic. Unit circle, and you've got a point right here. So if I go out, let me give this guy a little bit of red. If I go out here and I make a triangle with that, so this side here, my x is basically cosine of theta. Here's my angle theta, it's in the middle there. Maybe I'll make that blue just to make it clearer. There's theta. That's theta. It's not my cleanest theta, but it's theta. That's the angle. We said that the y in the unit circle is your sine. So, and hey, I've got a right triangle here. This is looking awfully familiar. I've got one side of a right, one leg of a right triangle, another leg of a right triangle, and then this, on a unit circle, we know that the hypotenuse is 1. So really what we've got here, and kind of going back to this whole idea of Pythagorean identities, is that my x squared, because cosine squared of theta plus sine squared of theta is equal to 1, because this is your x squared plus y squared equals 1. We've seen this before, it's just in a slightly different format because we're looking at the unit circle right now. Again, important thing to remember about the unit circle is that your radius of the circle is 1. That means that the hypotenuse of any triangle that you form in there is going to be 1. And these are just the legs. This is good old a squared plus b squared equals c squared. So that's how that one is true. And once we know that, that's actually pretty powerful. We can take a look at our next one here. The next two are actually very similar, but 1 plus tangent squared of theta is equal to secant squared of theta. Let's see how that one can play out. 1 plus tangent squared of theta is equal to secant squared of theta. So let's simplify what we have on the left. If I'm going to add these together, let's put this tangent squared theta, we can rewrite this as sine squared of theta over cosine squared of theta. Why can we do this? Well, think about this. Really what you've got here is tangent of theta times tangent of theta. And that is sine of theta over cosine of theta times sine of theta over cosine of theta. And if you multiply across, that will give you sine squared of theta over cosine squared theta. So we can substitute, and if we're going to add these two together, 1 plus this, we can also do some substitution for 1. And if I want to add these two together, I need to have like denominators. So I know that I'm going to have cosine squared of theta in the denominator, and the only way to get that and preserve the value of having 1 is to have cosine squared theta as the numerator, because cosine squared theta divided by cosine squared theta is 1. Anything divided by itself is 1. Let's also rewrite this secant squared theta. This is the same thing as 1 over cosine squared theta. So now this is starting to look pretty nice. I've got everything here with the denominator of cosine squared theta. Let's add them up. So cosine squared theta plus sine squared theta over cosine squared theta. I preserve the denominator. They've got to have the same denominator. I'm just adding here. I'm not multiplying. That's why the denominator stays the same. And then we just added the top together. We're just adding fractions. Equals 1 over cosine squared theta. And then here, this we just saw moments ago back here, that if I add sine squared theta plus cosine squared theta, that will give me 1. I have that here, so I can substitute, and I can say that 1 over cosine squared theta equals, well, 1 over cosine squared theta. That's it. That's why it's true. We can do the same thing for this guy here as well, except instead of everything being over cosine, it would be over sine. Let's take a look at one last batch. We're going to look at the confunction identities. And basically what these are saying is that if I've got a sine or cosine function or even tangent function, if I take whatever my input is for that and I subtract that from pi over 2, that's going to give me, if I do that for sine, it gives me cosine. If I do that for cosine, it gives me sine. And if I do that for tangent, it gives me cotangent. Let's look and see how this works. So notice that if I look at my graph here, the sine is in red, the cosine is in blue. If I shift my sine a little bit to the left, exactly pi over 2 to the left, it's going to match up. It's going to layer right on top of that cosine. Essentially, they are the same function pretty much, just a slide, a horizontal slide of pi over 2 from one another. And we can see this with the table over here as well. So if I have pi over 2 for my input, I can, for sine I have 1. If we take pi over 2 minus that gives me the cosine of theta. So if I have pi over 2 minus pi over 2, that's really the sine of 0. And the sine of 0 is 0. So effectively, what this is doing is it is moving our, in this particular table, because my increments are all pi over 2, it's moving one step back, because we're going back pi over 2. And that's really it. Again, let me just do one more example here just to kind of show you how this works. If I've got let's do sine of, or let's do cosine. Let's do the cosine of, actually I do like sine better. This cosine's even. Let's do the sine of 2 pi. Okay, if this is, our thing holds true, then the sine of pi over 2 minus 2 pi should give us the cosine of 2 pi. Pardon me, I'm sorry. What I wanted to say earlier here was, let's look at the cosine of 2 pi. I apologize for that. Alright, cosine of 2 pi. So the sine of pi over 2 minus 2 pi is actually the sine of negative 3 pi over 2. Should equal the cosine of 2 pi. And yes, I don't have this conveniently on my table up here, but remember, since sine is an odd function, that the sine of negative 3 pi over 2 is going to equal negative sine of 3 pi over 2. So I can substitute, I can say this is going to be negative sine of 3 pi over 2 is equal to cosine of 2 pi. Sine of 3 pi over 2, we can go back to our table, which is negative 1 right here. So negative 1 is equal to the cosine of 2 pi. 1 is equal to the cosine of 2 pi, and remember, cosine of 2 pi is actually just right there, 1. So 1 equals 1, and everything checks. We're all set. So take a look, particularly focus on these Pythagorean identities, as well as the confunction identities, which are really just slides. Okay, horizontal slides to the, by a magnitude of pi over 2. Okay, bring your questions. Have a great day.